Okay, I hear the recording in progress, so we'll share the screen as usual. So we're doing 11.2, which is on series. Okay, one particular series we're doing is a geometric series. That's not the only series that we're doing in this section. Okay, and that isn't the only series there is. Obviously, there's a lot more, as you can see. Okay, so schedule-wise, we're just about right on schedule, starting 11.2, a couple days for 11.2. Okay. All right, so let's continue on with series. So my take on series, you can ignore any date that's up here. So we'll write summation, the sigma symbol, n equals 1 to infinity. Or if we're lazy, we know we're going to infinity, just quickly write summation of a sub n. Okay, so we add up the terms of an infinite series. Normally, we begin indexing at 1, but you don't have to. Maybe 1's not allowed for some reason, then you start indexing at 2 or 3. Later on, in our last sections, we'll index almost exclusively starting at 0, n equals 0 to infinity. Oh, so what's the difference between a sequence and a series? Sequence, A1, comma, A2, comma, A3, you're just writing them all out. For series, it's A1 plus A2 plus A3, you're adding them all up. You're adding infinitely many terms. Okay, so how do you add up infinitely many terms? Well, you see if the partial sums, okay, in other words, you take this, and then you take that, and then you take that as a sequence, does that converge to any one number? Okay, one particular type of series is a geometric series, okay, where there's a common ratio R. So after the first term, you keep multiplying by the same thing all the way throughout. Okay, the formula for the infinite sum, you can put this on your cheat sheet. S is A over 1 minus R. A is the first term, R is the common ratio. That formula works if R is between -1 and 1. Another way to write that is absolute value of R is less than 1. Otherwise, the series diverges. We do not approach any real number. Okay, so converge, diverge. Converge, you get a real number. Diverge, you do not get a real number. Okay, so I'll show you a bunch of examples right now, and I'll get you used to some of my abbreviations. Okay, 11.2, number 17. 3 minus 4 plus 16 thirds minus 64 over 9. Okay, and by the way, when the series alternates like this, plus minus, it's a good guess that the common ratio will be negative, right? Because as you multiply negative quantities, it'll flip-flop between positive and negative, right? Okay, so the common ratio is -4 thirds. And if you have a hard time seeing that, you can just take the second term and divide it by the first term. You just go -4 divided by 3 is -4 thirds. All right, so that is not between -1 and 1, so the series automatically diverges. Okay, and our abbreviation is SD for series diverges. Okay, so rather than writing the whole thing out, SERIES, DIVERGES, and series converges, SERIES, CONVERGES. By the way, you might think that's being lazy. You can probably write it once, but when you have to write it many times, like on the homework, if you have to do it over and over and over again, believe me, you want to have abbreviations. Okay, so our abbreviation for series diverges is SD, and for series converges, we'll put SC. Okay, so SD, we know it doesn't mean, San Diego or South Dakota or something like that. Series diverges, and SC, series converges. We know we're not talking about South Carolina or Southern California or something like that. Okay, so for us, SD is series diverges, SC, series converges. Okay. Okay, here's 19. 10 minus 2 plus 0.4 minus 0.08, and so on. Okay, the common ratio is -1/5. Again, if you don't recognize it right away, just take the second term and divide it by the first. -2 divided by 10 is -1/5. That's -0.2. That is between -1 and 1. So the series converges. I use the formula A over 1 minus R. First term divided by 1 minus the common ratio. So 10 over 1 minus a -0.2. That's 10 divided by 1.2, or 100 divided by 12, which reduces to 25 over 3. So this series converges to 25 over 3. This one does not converge. And by the way, there's nothing preventing you from plugging into the formula. Okay. you could do A over 1 minus R for this problem. It won't mean anything because we already know the series diverges. So this formula only works if R is between -1 and 1, or absolute value of R is less than 1. Okay, 21 star. And that reminds me, I'm not sure if I showed you the homework problems yet, so let me go ahead with that. For those who don't have the book and aren't getting it. So what are we doing? 11.2, 17 to 63. Okay, so page 716. 17, 27. I have to raise it up, sorry, to see 35, 37 way at the end there. There's that, and that. And goes up to 63. I think that's it. Yeah, 63 was the highest. Okay, 21 star. Summation n equals 1 to infinity of 6 times 0.9 to the n minus 1. Okay, so I plug in 1. I have 0.9 to the 0 is 1, so 6. Plug in 2, 6 times 0.9, 5.4. Plug in 3, 6 times 0.9 squared, 4.86. So the common ratio is 0.9. Okay, and a heads up, when you see stuff like this, quite often for a geometric series, the thing inside the parentheses will be your common ratio. It's not a guarantee, but it's something to look out for. It happens a lot. It's the best way to say it. All right, common ratio is 0.9. So what's really happening is that the R is between -1 and 1. The terms decrease in absolute value. You're getting smaller in absolute value. 6, 5.4, 4.86. They're getting smaller. Now, if R is outside of that range, like this, the terms are getting bigger in absolute value, so we don't approach any one number. So I can use a formula. The infinite sum is by formula A over 1 minus R. Again, put it on your formula sheet. A over 1 minus R. So 6 over 1 minus 0.9. That's 6 divided by 0.1, 60. And by the way, you could actually do this simulation, I guess, even in a spreadsheet. You could add up a whole bunch of terms, 100 terms, 1,000 terms, 1,000,000 terms. It'll get real close to 60. Okay, another starred problem, 25 star. Let me just see something here. Yeah, well, conceptually, it's similar to the one we've got. Okay, summation n equals 0 to infinity. Notice they start at 0 this time. Pi to the n over 3 to the n plus 1. Okay, so I plug in 1. Oh, sorry, plug in 0. I have 1 over 3. Plug in 1, I have pi over 3 squared. Plug in 2, pi squared over 27. So the common ratio is pi over 3. And again, when they have it like this, it's a good guess that pi over 3 would be the common ratio. Okay, so if you take this, multiply by pi over 3, you get that. Multiply that by pi over 3, you get that, and so on. Okay, pi is like 3.14. If I divide it by 3, it's a little bit bigger than 1. Therefore, the series diverges. (31 star). This is actually not geometric, but I can split it into 2. I can split the sum into 1 over 3 to the n plus 2 to the n over 3 to the n. Okay? And just like for the integrals, where I broke up the original I into I1 and I2, I can break up the series into S1 plus S2. Okay? So I'll just find this sum, add it to this sum, and I'll get the total sum, provided both of these converge. Now, if one of these diverges, then we can't say. but they both converge, as we shall see. So I take a timeout and figure out S1, figure out S2, and then put them back together. So how do I get S1? We'll just write some terms out. But again, we highly suspect the common ratio is 1/3. Plug in 1, you have 1/3. Plug in 2, 1/9. Plug in 3, 1/27. So yes, indeed, the common ratio, the number that you keep multiplying by as you go through the series, is 1/3. That is between -1 and 1. So I can use the formula. Infinite sum is A over 1 minus R, first term, 1/3, over 1 minus the common ratio, which is also 1/3. 1/3 divided by 2/3, cancel the 3's, 1/2. So this infinite sum is a half. Now I do S2. Well, plug in 1, you have 2/3. Plug in 2, you have 2/3 squared, which is 4/9. Plug in 3, 8/27. So the common ratio is 2/3. That's between -1 and 1, so the series converges. Use a formula. S2 is A over 1 minus R. First term is 2/3 divided by 1 minus R, which is also 2/3. 2/3 divided by 1/3, cancel the 3's out, 2. So now I have my infinite sum S as the sum of the two, S1 plus S2. Remember when we were doing the integrals, right? Same kind of thing. So, okay, I can break this integral up into 2 different integrals or 3 different integrals, work them all out, and then put them all back together. Okay, so I break up the original series into 2 other series, S1 and S2. So I figured S1 was a half, S2 is 2, add them together, 2.5. And then I got it. Okay. And check something in this chat. Why are you solving for 3 terms instead of 5? I'm not quite sure what the context is for that. Yeah, I'm not sure I understand your question. Yeah, so you can see me during office hours or send me an email. I'm not quite sure what you mean by that. Okay. If you're talking about how many terms that I write out, okay, I just have to write enough terms so I know what's going on. Okay, so here I know right away what's going on. So common ratio is 1/3. I mean, usually it's not enough to tell just by putting 2 terms, but if you want to say write down more terms, you may. There was a homework that said write the first 5 terms of this sequence, okay, but that was then. Now we just need enough to know what's going on, and I think we've done that over here. Okay, so I could write more, but I could look at this pattern and say right away, oh yeah, I keep multiplying by 1/3, so I don't have to write the 4th or 5th term. Same thing here. I know what's going on. I keep multiplying by 2/3. Okay. All right. Something called the test for divergence, which I'll abbreviate TFD. So I'm digressing a little bit from geometric series. Page 713. You have a theorem. This is worth knowing. If you want to put this on your cheat sheet, you may. If the series is convergent, limit as n approaches infinity of a sub n equals 0. Okay. The text goes over a proof. I won't go over the proof, but I'll just say it is reasonable. The series converges. If you know the series converges, then the a sub n, the individual terms, have to approach 0. They get smaller and smaller and smaller in absolute value. The logical contrapositive of that, contrapositive in logic, means turn the if and then around and put nots. It's always logically equivalent to the original statement. So if the series converges, limit n approaching infinity of a sub n equals 0. Turn it around and negate. If I say the limit as n approaching infinity of a sub n is not 0, the series diverges. That's the test for divergence. It's in the bottom of 713. What the text has is correct. I'll give you my version, which I think is more compact, and it says the same thing. If the limit as n approaches infinity of a sub n does not exist, or the limit as n approaches infinity of a sub n is not 0, the series automatically diverges. Okay, I'll give you the Melvin-Hum variety, which says the same thing. So test for divergence, you may abbreviate TFD. Again, it's not really a matter of laziness. Okay, and you're going to have so many homework problems where you have to write this out. Okay, if I have to write test for divergence, TEST, FORDIVERG, I have to write it one time, 2 times, okay. But when you have to write it many, many times, you'll believe me, you'll know what I'm talking about. It's nice to have these abbreviations. Test for divergence, TFD. So here's a test for divergence. If A sub n does not approach 0, the series diverges, SD. So our abbreviation is A does not, X, not, no parking, no smoking, no left turn, whatever, right? So A sub n approaches 0. X means A sub n does not approach 0, which could include A sub n approaches some other real number, like 1 or pi, or A sub n doesn't approach anything. The series automatically diverges. That's called the test for divergence. I'll show you some homework problems involving that. Okay, so 29, which I think is also 29 star. Yeah, 29 star. So sorry, I'm giving you a lot of stars here, but it does tell you how to do the problem. And frankly, when you get down to it, many math teachers, they don't do problems from the homework. They just have their own examples, and then you go do the homework, right? So I'm just kind of giving you, anything I give you is extra, so to speak. And now I'm just doing what other instructors do, give you problems that are not in the homework, but tells you how to do it. Anyway, summation n-1 over 3n-1. This is A sub n. So what is the limit as n approaches infinity? Okay, you could do L'Hopital's rule. This is infinity over infinity. Okay, so the limit n approaches infinity is derivative of the top is 1, derivative of the bottom is 3, 1/3. You could also do the trick of dividing top and bottom by n. Remember that trick? And then going from there. All right, so A sub n approaches 1/3, which is not 0. Where'd it go? A sub n does not approach 0. Therefore, okay, another abbreviation, ... like that. In logic, this means therefore. So look at how compact our writing is. Therefore, SD, series diverges by test for divergence. A lot less writing than writing out series diverges by test for divergence. Okay, you might think it's lazy, but believe me, when you have a whole lot of these problems, you just want to come up with abbreviations that we all know we're talking about. SD, we know in our class it means series diverges. It doesn't mean South Dakota, San Diego, or something like that. Okay. All right. So the series diverges. What this really means in the long run, when I go way out in the series, it looks like 1/3 plus 1/3 plus 1/3 plus 1/3 plus 1/3 plus 1/3 infinitely many times. Well, that just blows up. That doesn't approach any number. Okay, so the series will diverge. Okay, here's 37. And believe it or not, I think that one actually is a match. Yes, this time it is a match. So what's the limit as n approaching infinity of ln n squared plus 1 over 2n squared plus 1? Okay, you can do L'Hopital's rule. You can play the game of dividing top and bottom by n squared. It works. Okay, now that we're past that, we'll just go straight to the answer. We'll just say, okay, for super big N, the plus 1 drops into insignificance. It's n squared divided by 2n squared, which is a half. So the A sub n's, the terms, approach ln of a half. That's not equal to 0. You can punch it in the calculator, there's no need to. Okay. The terms approach ln a half. So in the long run, it looks like ln half plus ln half plus ln half plus ln half infinitely many times. Well, that's not going to converge. That will diverge. So the series diverges by test for divergence. Okay. A lot of this chapter, you'll be giving a series, and you just say the series converges because blah, blah, blah. or the series diverges because blah, blah, blah. Okay, so that's what we're doing for quite a bit of this chapter. Okay, now for a word of caution. The converse to this statement is not true. So what is converse? Converse means you switch it around or put knots here and not here. It is not true that if a sub n approaches 0, the series converges. Okay, and that's a big bugaboo for a lot of students. This is true. If a sub n does not approach 0, series diverges. However, if a sub n does approach 0, that does not mean the series converges. Series might converge, the series might diverge. Okay, that's kind of tricky. This is not true. Okay. One example is something called the harmonic series. So I want you to make a note of the harmonic series. You say, what is the harmonic series? On page 713, it's the sum of the reciprocals of the positive integers. So harmonic series by definition, summation n equals 1 to infinity of 1 over n. 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. This is called the harmonic series. Okay, and a side note, if we were meeting face to face, I would make you memorize this. I don't think it's that hard to memorize. It's 1 over n. Okay. And warning that maybe your next teacher will make you memorize this. So be that as it may. Now, the terms definitely approach 0. 1 over n. Afterwards, 1 over a million, 1 over a billion, the terms approach 0. However, we're claiming this series actually diverges. I'll give you an outline of a proof. There's a better proof in the next chapter why this works. But believe it or not, this series blows up. The individual terms approach 0, no question about it, or limit as n approaches infinity of a sub n is 0. This thing blows up. Okay, so I'll try to show you a little bit of the outline. Here are some partial sums. S2 is 1 plus a half. S4 is 1 plus a half plus this. That's bigger than 1 plus a half plus a fourth plus a fourth. They replaced that 1/3 with 1/4. 1/3 is bigger than 1/4. Essentially, they've added another half. S8 is 1/2, 1 plus a half plus a third plus a fourth, plus a fifth, sixth, seventh, and eighth. That's bigger than 1 plus a half plus a half plus 1/8, 1/8, 1/8, 1/8. 1/5 is bigger than 1/8. 1/6 is bigger than 1/8. 1/7 is bigger than 1/8. And 1/8 is equal to 1/8. Okay. So this top sum is bigger than this sum. Here's another half. Play the same game with S16. Write it like so. So you have 1 plus a half plus these two guys plus these two. This is 1/9, 1/10, 1/11, all the way to 1/16. That's certainly bigger than this. Same. 1/3 is bigger than 1/4. Same. 1/5 is bigger than 1/8. 1/6 is bigger. 1/7 is bigger. Same. 1/9 is bigger than 1/16. 1/10 is bigger than 1/16. 1/11 is bigger than 1/16. ... 1/16 is equal to 1/16. So when I compare terms here and here, they're either the same or the top number is bigger than the smaller. So that sum is bigger. And ultimately, I've added another half. There's a half. There's a half. There's a half. Basically, you can add as many halves as you want. So if I can add infinitely many halves, that diverges, in fact, to infinity. Okay, so this shows that the harmonic series diverges. Okay, so an interesting conclusion. This is a quote unquote famous series, not famous in the general public, but for us, hopefully. This is a perfect example of a series where the terms approach 0, but the sum goes to infinity, believe it or not. It goes to infinity very slowly, but it does go to infinity. Okay, so that's called the harmonic series. Okay, on page 714, here's some theorems. They do seem reasonable. It's almost like a distributive property we have. If A sub n and B sub n, notice the lazy notation is acceptable. They don't bother to put n equals 1 to infinity or whatever. We just want to talk quickly about a series. Then don't even bother putting the n and stuff. Just write it. Okay, if these two are convergent, then summation C A sub n, where C is a constant, also converges. So summation of C, let's say C is 2, A sub n equals C summation A sub n. And you can factor out the C. It's basically the distributive property. So in other words, suppose you know that this sum to the right of my pen is 5. Put a 2 in front. Well, the sum converges to 2 times 5, 10. And these two seem reasonable. Sort of looks like the commutative property. Summation of A sub n plus B sub n. You can split it up. I already did an example of that. Sum of A sub n plus sum of B sub n. And likewise, summation of A sub n minus B sub n, sum of A sub n minus sum of B sub n. Okay. So we have that. Problem 27. I don't think that one was starred. Let me check. Yeah. So is it convergent or divergent? 1/3, 1/6, 1/9, 1/12. If I factor out a 1/3, 1 plus a half plus 1/3 plus 1/4, this is my harmonic series. So 1/3 summation 1 over n. Now, what do I know about summation 1 over n? It diverges. In fact, it goes to infinity. I have 1/3 of that. It's still going to go to infinity. Not as fast, but it still goes to infinity. So the series diverges because I have a variation of the harmonic series. Series diverges. Okay. So that's what we have. Okay, now we have some problems at the end. Like 51 and on, express the number as a ratio of integers. Okay, you are giving a repeating decimal. How do I change a repeating decimal into a fraction? Right? Now, you may have learned techniques from this before. Do it the way we're showing you in class now, okay? Because we're learning about infinite geometric series. Okay, we have some. Yes, I'll show you some even ones. 0.46, the bar means repeat, right? So 0.464646. Write it as an infinite series, 0.46, 0.0046, 0.00046, and so on. So the common ratio is 0.01. So I use a formula. Infinite sum is A over 1 minus R, 0.46 over 1 minus 0.01, 0.46 over 0.99, 46 over 99. That's very easy to check. 46 divided by 99. Here we are, 0.46464646. Okay. It's very easy to do the arithmetic to get a repeating decimal. 46 over 99 is that. It's not so easy to go backwards, right? Now you may have learned some techniques in going backwards, but do it this way, in techniques of an infinite series. And of course, you can always double check your answer by working it back out. 54 star, I guess. It's 54 star. No, it's actually 54. 10.135 repeating. So separate out the part that doesn't repeat, 10. Then it's 0.135 plus 0.000135 plus 0.000000135. So the common ratio is 0.001. So the sum is separate out to 10 and then do the infinite geometric series stuff. A over 1 minus R, 0.135 over 1 minus 0.001. That's 10 plus 0.135 over 0.999, which is 10 plus 135 over 999. The question asks for the ratio of two integers. The rest is just arithmetic. Okay, both the numerator and the denominator are divisible by 9 because the sum of the digits is divisible by 9. Remember, rule of divisibility by 9, 1 plus 3 plus 5 is 9. Therefore, the top is divisible by 9. 9 plus 9 plus 9 is 27. That's divisible by 9. So I can divide out a 9. Yeah. 15 over 111. Both of these is divisible by 3 because the sum of the digits is divisible by 3. So that gives me 10 and 5 over 37. Final answer, 375 over 37 is the ratio of two integers reduced. 375 divided by 37 is the answer. And we can check that very easily. 375 divided by 37. 10.135, 135, 135, and so on. We have there. Okay. Now, excuse me. Oh, I see. I actually did. I did a 54 star. The actual 54 is a little bit different. 10.135 is repeating. So the bar is only over the 35. The 35 is the repeating unit. So that's 10.1 plus 0.035 plus 0.00035 and so on. So the common ratio is 1/100th or 0.01. Go from there, 0.01. So the sum is 10.1 plus A over 1 minus R. The geometric part is here, 0.035 over 1 minus 0.01. That's 0.035 divided by 0.990. Move over 3 spaces, move over 3 spaces. The rest is arithmetic. 101 over 10 plus 35 over 990. These are both divisible by 5, so I divide out to 5, that's a 7 there. So it's 101 over 10 plus 7 over 198. You can do the arithmetic. I know after a while we don't even like doing arithmetic. But you can get a common denominator, 101 over 10 plus 7 over 198. Multiply this side by 198 over 198, 10 over 10. Clean it up and reduce. 5017 over 495. Okay. So you can see that's quite a bit for this one. Okay, that's as much as I was going to do for today. So I'm actually pretty close to finishing the section. I just have the ones at the bottom, 57 and on. So tomorrow I'll do 57 and on, get that out of the way. Then I can probably get started with section 3. So I'm slightly ahead. On the original docket, I was going to finish 11.2 tomorrow, which I will, but it won't take the entire time for that. So I'll more than likely sneak in some of 11.3 also. Okay. All right. So otherwise, I think that was going to be it for today, folks. So let me check if anybody has any questions. Can you put the chat in there? Check the chat here. Yeah, I think I've caught up. Okay. Any questions, please? All right. Then we will adjourn for today. Okay. Have a good day, everybody. See you next time.
Thank you.
Take care.
All right.
Thank you.
Thank you. Bye.